Thank you everyone for the invitation to this seminar series, and thank you for coping with my delay. As we are going to be speaking about delays, I think it's very convenient that my train have been late. So what I am not really sure about the background of everyone here, so I have tried to start from a low level, but maybe it's always difficult to find what is low level for everyone, not? In particular when you have different backgrounds. So please feel free to stop me or ask me for further details or anything. So what I have thought is just giving you a kind of an overview of the different stability techniques that we use in control theory and how they can be applied to absolute stability of this bilateral teleoperation, thinking always from, maybe not from a robotic point of view, but thinking more from a control system point of view. So the task or the problem that we are going to set up is that, okay, we have a distance between the user and the robot, and then we want to overcome this distance by providing some kind of feedback to the user. So we want to teleoperate the robot in a distance, but actually we also want to send back some information to the user. A nice information that we can provide is trying to provide haptic feedback. Therefore, we reduce the cognitive load. It is not all based on images. It's also getting a little bit more of tactile information about the environment. So the aim of the problem, or the aim of this classical type of bilateral teleoperation is we want to increase the awareness of the operator. We want to increase evidently the performance of the operator, and we want to reduce the completion time for each of the tasks that the operator is doing. In bilateral teleoperation, we have these two measurements. One is performance in terms of tracking, how good the robot is following the command that I am providing. The other one is transparency. And transparency, sometimes we put it in the back of the problem just because we don't have as good tools as we have for stability. But yeah, it's a continuous fight between transparency and tracking performance, because we will put a controller, and then the controller will modify things to ensure stability. But by ensuring stability, what we are going to do is killing the transparency of the system. The challenges that we have is that it is very difficult to define a human mathematically. It is very difficult to define the environment, how the environment is going to react to the different contact that we are going to have. Therefore, we are going to have always this trade-off between stability and transparency, because if our controller is very good and is ensuring the stability, maybe our controller is going to introduce a new set of forces that are not forces that are coming from the environment, are just virtual forces that the controller is producing in order to ensure that everything behaves properly. And evidently, the main problem is that we are going to have a delay between the master and the slave, and the delay is going to be in closed loop because the signal are going to be flying. What happened in the master or in the local side will go to the remote side. What the remote side feel will go back to the master side, and then we are expecting the human to change the activity based on what the human is feeling, not? And what the human is feeling is coming from the other side, from the remote side, and this will produce a delay in the loop. And as we will see, the delay is one of the main issues that we have in a control system, or why the control system can behave in an unstable way. So I will assume that everyone here is familiar with this type of formulation of a robot. Yes? So when we want to express mathematically a robot, so in terms of a dynamic behavior, when we want to make the relationship between the forces and how the robot moves, these are kind of the standard equation that we always use, and it's just coming from the classic mechanics, not? And the mass, m, is a generalized mass that will contain the mass of the different links and the moment of inertia and all these parameters that we have in physics. The c is the combination between the Coriolis effect when we have a rotation, because a robot normally we will have rotation links. So the C matrix here is the combination between these two different effects. And what we are going to have there, this C can be obtained kind of algorithmically with simple equations. And finally, we have the gravitational effect, G, that is going to give me, for different configuration of the robot, what is the gravity trying to do in this term here. In our problem, in the master side, we will, or in the local side, we will have the interaction between the force produced by the human and the forces that in the master, if we have a haptic controller, the haptic controller can produce their own forces by itself. So we will have this kind of subtraction between if we have a haptic joystick, the human will be trying to move the joystick, and in addition, the joystick will be generating forces against the movement of the human. On the other side, we have a robot with exactly the same equation of motion, and then we will have the robot will be performing some, so we will have a controller telling the robot what are the torques in every motor, or what is the force in every prismatic joint that you have, minus the force that the environment is doing on the robot. Not? This is the term. This is why here we are splitting these forces in two parts. One will be just generated by the contact of the robot with the environment. The other one is the force that normally the controller will be generating, or that every of the joint is going to be producing. Normally we use, because we can have angles and prismatic variables, so we can have, if you have a prismatic joint, you will be speaking about a translation, but if you have a rotation joint, you will be speaking about an angle. In order to be using both translation and rotation in just one single symbol, normally we use the symbol Q just to represent all the vector with all the different joint of my robot. So far, so good? Yep. Okay. So a few properties. Maybe the most important there for us today is going to be the second one. So the first property there is just telling you that for any configuration of the robot, the mass of the robot is going to be always positive and always bounded by some number. It's not going to go to infinity as you go to a configuration of the robot. So it's always going to be bounded. The nice thing of this is sometimes if you want to do something like inverse dynamic, you may want to invert this matrix, but as this matrix is positive, then you can always invert it with this property. The second property, that is the one that we are going to be using today, tells me that the relationship, or if I consider the robot as a system with input velocity and with output torque, this system is going to be passive. So this guy here is not able to produce energy by itself. The robot will start with some energy, but the robot will not be able to produce energy by itself. evidently the only energy that the robot can start to have is the energy that the input is giving me, and in this case the input is the velocities of the robot. The third equation that we are not going to use in it today, but that is sometimes important in particular because a lot of configuration in robotics you will be doing adaptive control. So you will start with an initial set of parameters of your robot, but then you will provide an adaptation law where actually you are going to be improving the parameters that you believe. You will have a nominal set of parameters, you start your experiment, and then normally you will try to improve these parameters. And it is important that for this kind of problem, where you have this adaptation law, it is nice to write all these differential equations that we have here. It is nice to write it as one matrix that we call the regressor multiplied with all the set of parameters, zeta. And in the set of parameters, you are going to put the mass of the body, the friction of the parameter that you don't know about or that you have a nominal value, but actually these parameters can be changing. And this is why this last property, it is of significant in robotics. So the assumption that we are going to consider here is that both the human and the environment are going to be passive. So evidently we know that a human is not passive because the human will be able to introduce energy in the system. But what we mean there is if a human holds an object and the object starts to vibrate, the human naturally will try to fix it, will try to actually just remove energy from the vibration. So this is the assumption that we do in the human side, and we are assuming also that the environment is not going to be kicking your robot. The only thing that you can do, the environment, is to kind of produce a reactive force on you. So you produce a force on the environment, you touch something, whatever you touch, this force comes back to you. So the environment is not a source of energy, basically. Also, we will assume that all these gravitational terms will disappear. You can do that either by design of your robot, so you don't have a gravitational term mechanically, or basically you can implement an algorithm, you can implement a new definition of your torque or your force that actually is able to remove the gravity term. This is kind of very standard if you do feedback linearization. And here we are going to assume that all the times are constant. There is a lot of work also trying to play with time varying time delays. You will need other kind of rules, other kind of techniques, but evidently what we are going to assume today here is just the initial. Let's assume that the delay is constant. This is going to be important. We will go back later to this. So let me start with a little bit of control theory. So the definition, when you have an interconnection between systems, when we have this interconnection here between a plant and a controller, or between two different systems that are together in negative feedback interconnection, what we are expecting is, okay, if we introduce a finite amount of energy in R1 and R2, then the energy that the system is going to produce as an output, normally the output is Y1 and Y2, but you also can consider your output to be U1 and U2. The amount of energy in the output is going to be bounded by the energy that I introduce in the input. So if I introduce, I don't know, 5 units of energy, my controller will not be able, with this 5 unit of energy, will not be able to actually to produce more and more and more energy. It is going to be bounded. this kind of an input-output stability thing, and you can define this properly. I am not going to go into the definition of what is energy bounded, but there is a mathematical definition for a signal. You give me a signal, and I always can find what is the energy of this signal. So the Nyquist theorem, are you familiar with the Nyquist theorem? Yeah? So basically it tells you that the loop transfer function, so the product of P and C, if P and C are both stable, a simplified version of the Nyquist theorem is if you don't encircle the point -1, okay, your loop is going to be stable. So in this you can have a more general Nyquist theorem when either P or C or both are unstable, but for us we can put this kind of condition. First, let's assume that P and C are stable. So if I don't encircle the point -1 in the Nyquist plot, then the system is going to be stable. So this is the classical kind of Nyquist plot, and then I have the point -1 here. I need to make sure that this curve doesn't go around the -1, doesn't encircle the -1. When in the classical undergraduate course, you will have two important definitions for this, for the robustness or for a measurement of how much the stability of your system. These two guys are the phase margin and the gain margin. These two guys tell you, okay, if your loop suddenly increase the gain with a gain margin GM, then you will arrive from this point to the -1 and your system will become unstable, not? So the gain margin, it tells you how much gain you can introduce into the loop without going unstable. On the same thing, you have the phase margin. The phase margin is defined where the loop transfer function, when the loop transfer function touch the circle -1. At this point, this angle here is called the phase margin. And actually the phase margin is telling you how much delay you can accommodate in your loop before you become unstable. Okay? The delay is just giving you some phase in your transfer function, is increasing the phase of the transfer function, and the phase margin is kind of related to the delay that you can accommodate into the system. So always when you have a finite phase margin, you will be able to accommodate a finite amount of delay in your loop given by the frequency where you are touching the -1. So far so good. Any question about this?
Yeah, quick one.
Yeah.
By delay, do you mean lag?
Yes, I mean exponential of minus STD. Yeah, I mean time delay, a lag in a system.
Yeah, I mean, as opposed to process time delay, where it's just nothing happens until the delay is finished. I think you mean the lag, the phase lag, so you can accommodate a certain amount of phase lag in the system.
Yeah, I mean, it's phase lag, but a delay is producing a phase lag, no?
Okay.
I am thinking, yeah, it's lag, but I am thinking in terms of how much delay, because the delay is going to give you, sorry, I cannot write here. I feel a little bit encapsulated. But yeah, we can come back later to this.
Is process time, how much process time delay that
Yeah, I mean,
will affect the amount of lag that's in the system, and this is showing you the lag
yeah.
that you can accommodate.
Yeah, exactly. I am just trying to, because we are going to be speaking a lot about delay. I am just trying to just speak about delay. But yes, any lag in the system, anything that produces a lag, there it will move you to the -1.
All right, thank you.
Any other question? So this is the first situation that we can have. Sorry for my drawing skills. So if you have anything, any plan that you give me, but you never escape the circle minus one, the circle 1 not, it is impossible for you. If you never escape this circle here of radius 1, you never can encircle the minus 1. You never, in order to encircle the minus 1, you need to go out and then come back, or at least you need to touch the circle. Okay? So basically, if always the product of your plant, for every frequency, the product of your plant with your controller or any two system that you are using, the magnitude of this is always lower than 1, you always will be doing something. I really don't care what you are doing inside. But what I can tell you for sure is that your system is going to be, your feedback system is going to be stable. Okay, and this small representation, this toy example, is actually the underpinning concept that we are going to be using later when we are defining the small gain theorem. Okay, because the small gain theorem, what is going to make sure is that the gain of each of the system, when you multiply the gain of each of the system, is always lower than 1, and the gain, we are going to define the gain of a system just like you can imagine, like the radius of around the Nyquist plot. Evidently, the problem of these theorems is that we want to use these theorems when we have a nonlinear system. So the interpretation is not going to be so simple like we can write here. We will need, if you want to really go into the interpretation and into the mathematical definition, then you need a little bit of analysis in your pocket to be able to cope with the mathematical formulation. But the concept is basically this. You can imagine like what you are going to ensure when we are speaking about the small gain theorem is we are going to ensure that my system never escape of this radius of this circle of radius 1, and therefore it is impossible for you to be unstable, because you, in order to encircle the minus 1, you need to escape for a little bit, at least the circle, not? Any question about this? What we can see here, in this situation, we will say that the system have infinite phase margin. If you have infinite phase margin, your system can accommodate any time delay that you put in your system. So basically, the time delay, the only thing that is going to be doing is taking one of these points and moving it like in a rotation, like in an arc. Not? It's always going to keep the same circle and then moving it from one point to another point. It's going to perform like a rotation. You can think of the time delay as performing rotation with different angles at different frequencies of this guy. So if you put any delay in this kind of feedback interconnection, or in feedback interconnection that have this property, you are always going to be stable, because you never can escape the circle minus 1. Okay? And in this situation, we say that we have infinite gain margin. The same we can have it with infinite gain margin, and it's when actually your system never touch the negative imaginary axis. Sorry, the negative real axis. If your system never, or if the Nyquist plot never touch this part of the real axis, that means that whatever is the gain is only going to make your system bigger or smaller, but you will never be able to cross this point. And evidently, if you don't cross the negative part of the real axis, it is impossible for you then to encircle minus 1. So in this kind of system, if you apply any gain that you want, the system will remain stable, just because every gain, the only thing that you are going to do with a gain is changing the scale of the axis, not? But the shape of the Nyquist plot is always going to be the same, you will never be able to encircle the -1. And basically, this is the underpinning concept of the passivity theorem. If you have two systems where both of them are always positive, both of them, the real part is between 0 or -90 and +90, the phase, the real part is always positive, then when you multiply, or when you have the addition of the phases of these two guys, you never can touch the 180 degrees. And again, this is the toy interpretation that we can do for KIT, but actually when we move to the nonlinear bit, we cannot use this kind of argument just because we will not have Nyquist plot, we will not have this configuration of linear system. We need to formulate things in a mathematical, in a slightly more complicated mathematical way, but the concept, you can imagine it as the same concept. Any question about this? Yeah.
I might be wrong here. I need to check my notes, but I thought for passivity we need the phase of the system to be no more greater than 90 degrees, because the plot you're showing us has negative real components, which violates positive realness.
So this will be not one system but two systems. Okay. In this diagram, I am assuming the phase of two systems. Okay, the phase of P, the plant, and the phase of the controller. Okay? If one of the system is between -90 and +90, and the other one is inside, strictly inside of -90 and +90, you will have this configuration. Do you understand? So what I mean, what you are telling me is, you know that the phase needs to be between -90 and +90, not? And the red line have negative real part. But the red line is actually the addition of two guys. And what you are going to tell me in the passivity theorem, okay, wait a second, if this guy, if P is always have phase that is between -90 and +90, and this guy, the controller, is always going to be between -90 and +90 strictly, okay? So you never touch at you are in one of the systems, will avoid the border basically. So you don't have the situation of 90 + 90, 180, or -90, -90, -180. You avoid this situation by asking one of the systems to be strictly, so be inside without touching the border, no? And this representation is the red line is the addition of the two phases. Okay? So you are right. If you say what is a passive system, if we just take P, then everything will be in the positive real part. Okay? But this diagram is just the addition of both of them, and it's the reason of why when you have the passivity theorem, then you are asking to each of them to be between -90 and +90, and then when you put it together, okay, then the phase never can reach the -180 degrees. And if you never reach the -180 degrees, then you are in this situation where you have an infinite gain margin. Okay? So in the same way that when we use the small gain theorem, we can accommodate any delay, when we use the passivity theorem, we can accommodate any gain in the system. Any other question?
So with this setup, the feedback loop that you show us where you have your plant and your controller, that means if you have any non-passive plant and the phase is above 90, you can actually compensate with the proper controller.
Yeah, I mean, well, evidently the Nyquist theorem is if only if. So you are making this is kind of simple result that you can think in linear system that ensure just by checking individual properties of one and the other one, okay, ensure that you are going to be in a situation where your loop needs to be stable, okay? Evidently, if you say, okay, one of my guys is not passive, then you need to see a little bit about the other one to see if the other one can compensate for the lack of passivity of the first one. Okay? So this kind of condition, what we are trying to do is splitting the loop into two parts, and then we are testing conditions that independently can ensure that my system is going to be stable. The nice thing of having independent condition, okay, you are going to be more conservative, but the nice thing is that then you are going to be modular, that you don't care about this system, you take away this system, you put another one with the same property, and the properties of the system remain in the stability region. Any other question? Do I have a clock around? Or are we fine of time? Yep. So something interesting to mention is that when we are using the small gain theorem, actually you don't care about positive or negative feedback interconnection, because the only difference between positive and negative feedback interconnection is that the critical point in negative feedback interconnection is the -1, the critical point for positive feedback interconnection is the +1. So actually you cannot encircle this guy, but you cannot encircle that other guy. So you keep the stability is holding for both positive and negative feedback interconnection. However, in the passivity theory, actually the -1 is of essence, not? Without the -1, because actually what we are making sure is that we never can encircle the -1. The +1 you can encircle, of course, but the -1 is the critical one that we are considering here. So when we are using the passivity theorem, the negative feedback interconnection becomes kind of very important. So when we move to nonlinear system, we can think of these two concepts about the passivity theorem or the small gain theorem as a dating tool for checking if two systems are compatible for having the same input and output, or they are not. If we imagine this feedback interconnection where suddenly we switch off the power of my nuclear plant, or I switch off the power of my input, okay? Suddenly the input goes to 0, and then what needs to happen here is that the input of the first system becomes minus the output of the second one, and the output of the first system becomes the input of the second system. So we are trying to think if there is this possible combination of input that actually can can fit the system in the right way. If you are able to find these two signals, U and Y, then you have there an oscillation between, without any energy, you have these two signals. Of course, what we want to prove is that the only signal that you can put there is U equal to 0 and Y equal to 0. If these are the only two signals that you can put in the loop, then you are done. When we are thinking in the passivity theorem, we are going to say, okay, I have signals, or I have systems that behave in such a way that the product of the input with the output is positive. Okay, let's assume that G have this property. The product of the input with the output is positive. Okay? But then if you move to the other side, phi, I am just putting phi because of convenience, but nothing interesting right now. It's just showing that can be nonlinear. If you move to the other side, and then you think about phi also being passive, then now you say, okay, my Y times minus U, now this have to be negative, because the first one is telling me that U times Y is positive. Therefore, when I move to the second one, if the second one is also passive, then I got here a contradiction, because the passivity will be telling me that U times minus U is positive, okay? But actually the first system is telling me that U times Y is positive. Therefore, we use this kind of contradiction to show that actually the only signal that can be there is the signal U and Y both equal to 0. This is what the passivity is doing. we can do exactly the same with the small gain theorem. So if we have u and y, what we are going to say, okay, let's assume that this g have norm equal to 1. So this will tell you, for example, that this expression here, that the energy of the output is always above, is always bounded by the energy of the input. But if you have the same property in phi, or if you know that the gain of phi is equal to 0.5, for example, because then the product of the gains will be 0.5, we will have stable behavior, then it is impossible that this is true, because you will have kind of the opposite condition. You will have that now the u need to be larger than the y. So you can think in a simple manner of these two concepts, passivity theorem and a small gain theorem, as we do with linear system. With nonlinear system, we need a different type of formulation that sometimes can be a little bit more convoluted, but the concept is more or less the same. Any question? And as we have been commenting, if we have a small gain theorem, so if we have a delay, my delay behaves very nicely as a small gain theorem, because the delay is not producing any amplification of my signal, it's not producing anything in my signal. The delay is only taking a signal that started at 0, and maybe now it's going to start at 5. But if we think in the energy of the signal is going to be after and before is going to be the same. So the delay is not producing. If the delay is constant, I have to say, if the delay is constant, the delay is not producing any kind of change in the shape of the signal, and the shape of the signal is basically what gives you the energy inside of the signal. So this is kind of the formulation of a passive systems when we have nonlinear system, because now we cannot go to the frequency domain, we need to stay in the time domain. And basically it's the classical formulation that you have seen if you have studied any kind of the circuit analysis, the passivity, the passive system RL, RC circuit node. You have this kind of, the product of the voltage times the current is always positive. The nice thing about passive system is when you interconnect passive systems, the result is also a passive system. And this gives you some nice properties that you can use in bilateral teleoperation. Again, as commented before, if you have a linear system, then instead of checking the integral of this guy for all the input and all the output that can be a little bit convoluted, you just need to check to produce the Nyquist plot and to check that the Nyquist plot always lands in the positive part. And as commented, when we are using passivity, we always will have this kind of strictly passive, and strictly passive means that you don't touch the border, because you want one of them to be passive and the other one to be strictly passive in order to converge to 0. Any question on that? So when we are trying to extrapolate this analysis to the passivity, to the feedback interconnection of bilateral teleoperation, we are thinking in this structure where we have the operator and the environment in both sides. These two guys, the operator and the environment, will be passive systems. And then what I need to ensure is that this block here, the combination of the local controller, the communication, and the slave controller or the remote controller, these three things as a block behave as a passive two-port interconnection, because if this guy here is passive, then the operator and the environment all together, none of the blocks can produce energy by its own. Therefore, you cannot have bad behavior or unstable behavior due to the delay. And the main technique that we need to use is this combination between passivity and small gain theorem. And it's due to, okay, we are thinking, we have in these two parts, operator and environment, both of them are passive, okay? But then in the center, we have something that is the communication, something that is the delay, that evidently is making the system non-passive. The delay cannot be non-passive. So what the trick that I am going to present now is a trick that just transform something that is not passive but is a small gain, because the delay is, okay, it's a non-passive system, but we know that the delay have a bounded gain. So what we are going to be using for this technique is that actually, because the passivity properties of the guys, we want to use passive in the side, outside. In the center, I have this delay that for sure is not going to be passive, because the phase of a delay is just the product of the time delay multiplied with the frequency. So for sure, this will look like a circle, basically, of radius 1 in the Nyquist plot. So therefore, this is not passive. But actually, what we can use is that the gain of the system is 1. And this is something that in control theory is called the scattering transformation. And the scattering transformation is that if you have a system that is passive, you always can produce a different system that is a small gain or half gain equal to 1. And this is if only if, so you can go in either direction. So what we are going to do is, okay, we know that in the center we are going to have something that is only a small gain. Then we are going to produce something in the left and something in the right of this system that is going to convert the small gain property into a passivity property, and then is where we are going to put the other bit in between. So you kind of, what this V and W there are called normally the wave variables. I think in the other slide I was using U and B. Sorry for the inconsistency between the slide. Any question about this? It's kind of the main trick when people is thinking about passivity configuration in bilateral teleoperation. I think is the main trick that they are doing. What they are doing is we have something that is a delay in the center. We have something that is not going to be passive. But what we are going to do is producing this kind of alternative formulation of the block in the middle that by a combination of the input and the output, so instead of sending the force or the velocity only, we are going to send a combination of the force and the velocity to the other side, and this combination of force and velocity are going to make that whatever we have in the center look like a passive system. Are we fine with time? 15? Okay. I think I have more than enough for that. So the wave transformation, that is something that people in communication use a lot when they are doing this kind of energy going through the system. So we are going to produce something like that look like this transformation. This is the scattering transformation in one side, the scattering transformation in the other side, and then in between I am going to have my time delay. And what this is allowing me to do is actually allowing me to kind of bound the energy that I am going to have in the communication. Not? So it is producing this kind of wave kind of delivery that I am going to be able to, with these two guys, with the integral between the past time delay up to now, I am able to actually to have this kind of bound. So this wave transformation is going to make sure that now I have a nice behavior between the wave variables and the. So here, it is a finite gain system. So this t, because it's a delay, it is bounded in terms of the gain. And then I am going to put these two other guys here and here that contain two scattering transformation, one in each side. And from this point and this point, when I encapsulate this in one single box, what I see from outside is kind of a passive system. Okay? And this is basically the tricks that we use. And it's kind of related to this concept of the scattering transformation in control theory, where you are jumping from a passive system to a small gain, or a system with bounded gain. So if we start from inside to outside, when we have the final type of transformation or the final standard configuration of these systems, we will start just by, in the middle, we just have a delay between these two guys and these two guys. So the wave are moving in the top left to right and right to left. Then we will have this scattering transformation that is given by these matrices. In this formulation, this block here, the scattering, have two input. The input will be the force in the master side and the wave in the master side. And the output will be the position that we decide, or that we are giving to the master device. And in the other side, we have exactly the same. The second output of the scattering transformation is the wave that must goes to the other side. Finally, what we are going to do is, once we know where we want the robot to be, what we are going to do is put in a spring damper between the position that we want the robot to be and the position where the robot is. The robot is in this position. The robot have to be, or for a nice control system, have to be in this position here. And then we are going to introduce a spring damper system between both of them. And these two equations are giving me the spring damper system between the velocity that I want the robot to have and the current velocity of the robot. And I am going to have the same type of controller in both sides. So because this kind of spring damper system, evidently this is linear and it's just a PI integrator. If you are familiar with control, the only thing that we are doing here is just a PD controller, or PI, depending on what you think as an input and an output. But in any case, this guy is going to be passive. This guy is also going to be passive. The block connecting these guys is passive for any delay, because what we are doing here is for any delay. Everything now becomes a passive system, and then we can introduce this concept. Okay? So it's basically this trick of the scattering transformation what allows you to actually to have something that per nature of the delay is non-passive, but actually what we are going to use, instead of using the passivity properties of the delay, what we use is the gain properties of the delay to transform something that have a gain of 1 into something that is passive. Yeah?
The scattering blocks, they accept control inputs and they transmit it to the other side. Yeah. The control inputs are generated by the positions and velocities of the master and the slave robot. would it work if we use human force and environment force directly in the scattering?
These forces are not, because you will need a force to move the key point here is that you mean that if instead of sending this force here, we send directly this force in the environment or this force in the human directly?
But of course that means we need to change the topology here.
Yeah, you need to change this. But in addition, another of the problem that you will have there is that evidently when you move in the local site, if you move your haptic joystick, the other guy will need to feel a force. And this force is not the force of the environment. It will be the force of the controller moving the robot because you are moving the robot. Do you understand? So actually this force here is kind of significant too, because it's the force that the robot in the other side needs to perform in order to follow the movement of my hand. No? So it's the environment, this force, will be just when the robot interacts with something, but the robot also needs to move. No? Do you understand? So this is the problem of sending direct. If you just send directly the force of the human, you will miss what the controller is doing to perform this kind of communication. Anyway, this is like called position feedback, position configuration. In other configurations, you can send actually the force of the environment, and it's called position force architectures. So you have like 2 channels, position. You have 3 channels when you are able to measure the force of the environment, and you have 4 channels if you are able to measure everything. But this configuration was developed for the standard 2 channel configuration. But there is a lot of literature trying to include also in the communication the force of the human and the force of the environment, and this gives you an additional information that you can use for solving the issue of transparency.
Joaquin,
yeah.
may I just point out, I don't know if you mentioned it, but one of the interesting things here is that the product of velocity and force, so you've got x dot, which is change of position. The product of velocity and force is power.
Yeah.
So the combination of these two is the power in and the power out. In other words, the rate of change of energy in the system.
Yeah, I mean,
so this configuration shows the power flow and the accumulation of energy in the system.
Yeah, I mean, it was kind of in a slide at the beginning when we were mentioning, it's kind of this equation here, not? Is the product of we are using this kind of
absolutely
power.
I just thought it was pointing out
this is the power, and therefore the integral of the power is the energy in the system. Thank you for that. So basically, after this, as a summary, what we are doing is performing a mathematical trick to make sure that this guy is within the nice assumption that we are going to do. So then the human is going to be connected to a simulated robot that then will have some kind of desired velocity. When we are sending the information from one side to the other side, we don't only use the force, we also use the velocity, and this is what allowed me to do the trick of keeping all these blocks in the passive interaction, and then in the slave side or in the remote side, I will have the same configuration where I will have a desired position or a desired velocity of my robot, and then I will have the real robot connected with a simulated spring that is in the other side, and this is how the controller is ensuring the stability of everything, because evidently these guys are stable and nice behave systems, and this trick that we are using with time delay is what is allowing me to actually ensure that the overall interconnection remain stable, or as Roger was mentioning, that the power is not generated there, so you have a finite amount of power, so once you switch off your controller, everything should go slightly to zero. I think I am going to leave it here. Any question about this last part?
Okay, this is Kai. Can you hear me?
Yeah.
Just a quick question about the assumption of the system. So in the nonlinear system case, are we still assuming that the time delay is constant?
In this config, if you just want to use this, you need to assume that the time delay is constant, because the gain of a time the gain of a delay is equal to 1 only if the time delay is constant. If the time delay is changing with time, then you need to use more sophisticated techniques. You need to take it away and use other kind of configuration, as Harun was doing during his PhD. Or it is done in the literature how to deal with this kind of system. But in the basic structure that we are putting here, the variable time delay may do that actually the communication doesn't have gain equal to 1, and therefore the scattering transformation is not going to work. But this is kind of the standard configuration. And as something that I should mention is that this is ensuring the stability, but actually the performance is very, very poor, and this is why this configuration was proposed at the beginning of the 90s, and there is plenty of research on how to improve the transparency of the system. Yeah.
How would you go around tuning the scattering on real hardware?
Tuning the scattering?
Yeah, how would you implement it on real hardware and get a response that you're happy with?
The scattering transformation is going to be always almost fixed by the desire that you want to have in the controller. So normally the standard configuration is that the dampers in each side of these two guys here have the same kind of reflection index that the communication. So actually the scattering transformation is called matching impedance. So you are trying to match the impedance of everything, so you don't have a reflection. It's like when you are connecting two cables, no? You will like the impedance of both of them to be the same, and then you don't have the reflection. So normally the standard assumption is that the dampers in each of the sides will have the same impedance, that the coefficient that you are selecting for the scattering transformation is the standard assumption. But again, if you have very, very different robots with very, very different impedance in each of the sides, maybe this is from a stability point of view is ensuring the stability, but maybe the performance is very, very poor.
Well, your last statement, you said this was developed in the 90s and there are now better ways to do things.
Yeah.
Just give us an opener into what better ways you would think about that.
So what we have been doing, again, in this configuration is trying to, or what people have been doing is, it was proposed at the beginning of the 2012, I think it's Pollard's thesis. It was when actually you split in a kind of Luret type of analysis, where you, instead of thinking of all the systems, all of them are passive, then you put it in a block, and then you produce a specific condition for each of the blocks. Not here we have the human, the environment, the delay in one direction, the delay in another direction. So then you can actually to exploit the structure of the whole feedback systems to put in one part of the block the bad things that you have, and then to put in the other part the linear part, or the things that you know very well and that you have a lot of information, and then trying to do something something like this. Something that also I should mention, we have been always thinking in control of the velocity. The control of the velocity have the risk that if you lose the communication for a while, you will have a natural drifting between the master and the slave. So there is a lot of research also trying to correct how you can correct this without killing the stability in this case when you also have information about the delay. So there are several different techniques trying to accommodate all the different issues that you can have in terms of communication, loss of data transmitted between master and slave, and the different problems. And of course, the main problem here is that we are always speaking, or someone like me is always speaking about the stability because it's what I do, and I really don't care about transparency when actually it's one of the main issues, not?
So in the lower structure, what is the definition of stability for that?
So in the lower structure, basically what you are going to do is kind of having what is called the IQC theorem, where you are going to have, it is kind of the same concept that previously. What we are trying to make sure is that the properties between the input and the output of this, so if you think of this guy and that guy as input and output, the properties of this input and output have to be different, or have to be in another different set than the properties of the input and the output of this other block. If these two guys are disjoint, if you cannot find common pair of input and output that then you can put in the other system as an output, as an input, then is where you are trying to find this kind of, so mathematically it will be something that look kind of this, and yeah, is kind of making sure that in one part this sign is always positive, in the other side, when you move to the other side, is strictly negative. Okay, so the main concept is always studying all the set of input and output of your system, of the pair of input and output of both systems, and making sure that there is no compatible input and output in these two sets of systems. This is what is called graph separation principle that was developed also in the 80s by Safonov, and what people have been doing in the last years is actually to improve the definition of these multipliers and to reduce the conservatives by using richer and richer definition of your class of the system, to be more precise when you are defining the system and when you are defining the environment.
Sounds like there's another entire lecture you could do on this. Maybe we have to get you back.
Yeah, it could be a little bit harder if we start to go into this. Just explaining all the symbols in this slide can take a while.
Thank you very much.
Okay, no worries. Thank you.